In this video, we will practice working out some AP exam style multiple choice questions pertaining to polynomial functions and complex zeros. This is AP Precalculus topic 1.5. If you appreciate this content, please help a brother out. Hit that like button. Number 1. The polynomial function p is given by p of x equals 3x times x plus 1 to the second power times the quantity x minus a, where a is a real number. Which of the following could be the graph of y equals p of x? If we could find the leading term of p of x, that would give us a lot of information to help us choose. We can find the leading term by considering only the leading term of each factor. So we will consider only the 3 of x, the x to the second power, and this x. Ignore the plus 1 and ignore the minus a. In that case, the leading term can be found by 3x times x to the second power times x. In other words, this is 3 times, I see 4 x's here, so 3x to the fourth power. Notice that this is an even degree, right? This is degree 4. We have learned in the past that an even degree polynomial has the same end behavior on the left and right. So either it's going to be 2 arms up like this, or both sides will be down like this. And we see that it is a positive leading coefficient, so we know the end behavior would look like this. Looking at options A and B, these have the end behavior of an odd degree polynomial with 1 arm down and 1 arm up. So the answer cannot be A or B. Both options C and D have the correct end behavior for even degree. So we're going to have to go further. Let's talk about the real zeros and multiplicity. Let's basically do a little bit of trial and error to figure out whether C or D is the answer. We can easily identify 2 real zeros of p of x. We know that one will be x equals 0 coming from this monomial in the front, and we know that x will equal negative 1 coming from the x plus 1, setting that equal to 0. There might be a third one. There might be x equals a if we set that equal to 0. I'm saying might because a could be any real number, including a might be 0. So it might not actually be another real 0. It could be x equals 0. Or, obviously, it could be negative 1. So it could be one of these. So it might not be a third real 0. In fact, we sort of know that the a has to be one of these two, because looking at our remaining choices, C and D only have the 2 real zeros. Option C has a 0 at negative 1 and 0 only, and option D has real zeros at negative 1 and 0 only. So there are no other real zeros. So A is either 0 or it's negative 1. So here comes the trial and error. What if A equals 0? In that case, p of x would equal 3x times x plus 1 squared times x minus 0. I'm just plugging in 0 for a. Obviously, x minus 0 is just x. If we simplify this down a little bit, we will have p of x equals 3x times this x is going to be 3x squared. So we'll have 3x squared times x plus 1 squared. So let's talk multiplicity. In this case, the 0 of x equals 0 will have multiplicity 2. Let me just add that in. This would be multiplicity 2. And that would leave the 0 of negative 1 to also have a multiplicity 2. This is coming from the exponents. So this would have a multiplicity 2. This will help us decide which one is the answer, because we've learned that if a 0 comes from a factor with multiplicity 2, then the graph is going to be tangent to the x-axis. It's going to do kind of a bounce off the x-axis at that particular 0. we say that the graph is tangent to the x-axis at that 0. So if both of these have multiplicity 2, we would see a bounce at 0 and a bounce at -1, tangent and another tangent. And that is exactly what we see. So because of that perfect match, I feel confident that the answer is D. Now, having said that, let's follow through on our trial and error and see what happens if we let a equal -1. If a equals -1, then p of x equals 3x times x plus 1 squared times x minus -1. I'm just plugging in a -1. Of course, minus a -1 is really plus 1. Written like this, we realize that this x plus 1 is just an extra factor of the x plus 1 squared that we already had. So there's really 3 of them. So we could write p of x this way. P of x equals 3x times x plus 1 to the 3rd power. In this case, the x equals 0 has a multiplicity of 1, because there's only one of them. And the x equals -1, coming from this factor, has a multiplicity of 3. Let's take a quick field trip to Desmos so I can show you what happens differently at a 0 with multiplicity 1 versus a 0 with multiplicity 3. And now I'm just making up a new function. I'm going to make up a function that has a 0 at -2. So let's say y equals x plus 2. Alright, so there I'm going to have a 0 at -2. I'm going to leave this multiplicity 1. Now I'm going to make the function have a 0 at +4. So I'm going to go ahead and give it an x minus 4. Okay? Now at the moment, both of these have a multiplicity of 1. So notice how the graph just goes right smoothly straight through each of these zeros. I already mentioned what happens if we have an even multiplicity. So as I make this multiplicity 2, notice that this now bounces off of that particular 0, and we say that the graph is tangent to the x-axis at that point. Now, as I increase this to 3, all right, making it odd again, you're going to see that the graph still passes through the graph. So any odd multiplicity, the function will pass through that particular 0. However, if it's multiplicity 1, the graph just goes straight through. But if it's multiplicity 3, it makes an inflection, like a point of inflection. All right, now out of curiosity, what if we make it a 5? Okay, still an inflection. What if we make it a 7? Still an inflection. So, for odd multiplicity, yes, the graph passes through the corresponding 0. But there is a difference between multiplicity 1 and all of the other odd multiplicities. Multiplicity 1, the graph goes straight through. Any other odd multiplicity, the graph has a point of inflection. Looking at option C, there are no points of inflection, so this would not fit. In fact, we see that the graph just goes straight through both of these zeros. That would only happen if the x plus 1 also had a multiplicity of only 1. And that's just simply not what we see. So the answer is D, like we said before. Number 2, the table gives the values of a polynomial function q for selected values of x. What is the degree of q? Since the input values have a common difference, we can use the differences of the output values to figure out the degree. The trick is, if the first differences are equal, then the degree is 1. If the second differences are constant, then the degree is 2. If the third differences are constant, then the degree is 3, and so on. So here are the first differences. They are not constant, so the degree is not 1. Let's keep going. The second differences are not equal either, so the degree is not 2. Wow, the third differences are not constant either, so the degree is not 3. Finally, the fourth differences are constant, so the degree is 4 and the answer is C. A polynomial function has the form p of x equals ax to the j plus bx to the k, where a and b are non-zero constants and j and k are non-negative integers. Which of the following conditions guarantees that p is an even function? A polynomial is even if every term has even degree. Note that 0 is an even number. For example, g of x equals 5x to the fourth power plus 7x squared plus 3 is an even function because all of the exponents are even. You see the 4 and you see the 2. What about the exponent here? Well, a constant is times x to the 0 power, and 0 is even as well. So, which one of these scenarios will guarantee that we have all even exponents? Well, what if k is equal to 0? So k is this exponent on the right, so what if that were 0? Well, that gives us one even exponent, as we know, but that leaves x free to have any exponent. J could be whatever it wants. J might be 3. So the fact that this is 0 does not guarantee this will be an even function, because j could be odd. So the answer is not A. What about option B? What if k is even, and then j is double that? Well, if k is any even number, like for example, if k is 4, k is right here. So if k is 4, then that means j would be 8. Alright, so if k is an even number, doubling it will give you another even number, and kabam, all the exponents are even. So B is the answer. Just for educational purposes, let's debunk the other two options. What if j plus k is an even number? Well, what if x is 1? What if j is 1 and k is 3? J plus k would be 4. That's an even number, but the exponents themselves are odd. So we just disproved C. What if j times k is an even number? Well, what if j is 1 and k is 4? 1 times 4 is 4, which is even. But j itself is odd, so we don't have all even exponents, so this would not be an even function. So D is not the answer. Number 4. The graph of the polynomial function y equals p of x is shown. Which of the following could define y equals p of x? And then we have some options down here. Let's examine the zeros. This function has two zeros. There's one at -3, and there's another 0 at 4. At x equals -3, the graph passes straight through, so we know that this 0 has multiplicity of 1. On the other hand, at x equals 4, the graph bounces off the x-axis, or we say the graph is tangent to the x-axis. That means that this 0 has even multiplicity. Turning these zeros into factors, I know I'm going to have an x plus 3, which would give me a 0 of -3. So there's going to be a factor of x plus 3 involved. There's going to be a factor of x minus 4 involved for sure. And then it's going to have even multiplicity. So this might be squared, or it could be to the 4th power or the 6th power. I'm noticing that all of my answers have 12s in the denominator, which doesn't change anything in terms of these values. All it does is makes the graph shorter. And they all have 12, so we can almost ignore it. I'll just go ahead and put a 12 down here. So I'm looking for something like this. The only difference is this exponent on the x minus 4 could be a 4 or 6. So let's see what we've got. x plus 3, x minus 4, even power. Okay, I see x plus 3, x minus 4, but the powers are not right. X plus 3 should have multiplicity 1. So, nope. Let's look at B. X plus 3 has a multiplicity of 1. The x minus 4 has an even multiplicity. So, I think the answer is B. I haven't looked at the other answers yet. But yeah, x plus 4 has a multiplicity of 1 right here. The multiplicity is all wrong here, so that's no. And looking at D, it should be an x minus 4, not an x plus 4. So that's no good. This should be x minus 4, this should be x plus 3. That's why this is wrong. So the answer is B. Kabam! Nailed it. Number 5. The function q is a polynomial of degree 3. If q at 5 equals 0, which means 5 is a 0 of the function, which of the following must be true? The fundamental theorem of algebra says that the degree equals the total number of zeros if you count the multiplicity as separate zeros. For example, if I see 1 0 but it has multiplicity 3, if I count that as 3 zeros, and including imaginary zeros. The degree gives you the total number of zeros. So for this problem, we are told that the degree is 3. So for one thing, that means q has 3 zeros. Now they told us that q at 5 equals 0. That's another way of saying that 5 is a 0 of q. So one of the zeros is x equals 5, which means that x minus 5 is going to be a factor. So let's start looking at these options and trying to figure out which of these options has to be true. Is it definitely true that negative 5 is also a 0 of the function? No, I think this is trying to trick us into thinking about conjugate pairs, which is something that happens with imaginary zeros. So for example, if we have 1 0, that is, say if we had a 0 of x equals 5i. Alright? If you have an imaginary 0, these always occur in conjugate pairs. So if 5i is a 0, then negative 5i is also going to be a 0. Or if we have a full complex number, like 3 plus 5i, if that's a 0, then 3 minus 5i is also a 0. But that only happens with imaginary numbers. So if you have a real number, like x equals 5, a real 0, that doesn't mean that you're automatically going to have negative 5 as another 0. So there's nothing in the information that tells us that this will be true. This does not have to be true. What about B? Q has 2 complex zeros. So, I mean, that's possible. We know we have 1 0 and there are 2 more zeros, unless the other zeros are a multiplicity of 5. But it could be 2 complex zeros, but there's nothing that tells us that it has to be 2 complex zeros. This does not have to be true. What about option C? Q of x can be expressed as x minus 5 times, that's what this is, times p of x, where p of x is a polynomial of degree 2. Option C is saying that q of x can be expressed as x minus 5 times some degree 2 polynomial. That is true. The answer is going to be C. Let's talk about it for one more second. We already said that x minus 5 was going to be a factor. So there you go. And if x minus 5 is a factor, and the overall degree of the polynomial has to be degree 3, well, if you multiply x minus 5 times any degree 2 polynomial, you're going to get degree 3. So that's true. Before we move on, let's talk about why D is not the answer. The problem is that if I divide like this, I will not necessarily get a polynomial at all. If p of x is a degree 4 polynomial, okay, for example, say if I had x to the fourth power, plus 3, and then I divide that by x minus 5, this is not a polynomial at all. This is a rational function. It's not a polynomial. So that's why the answer is not D. Number 6. The leading term of a polynomial function p is an times x to the n power, where an is a real number and n is a positive integer. The factors of p include x minus 3, x minus I, and x minus 2 plus I. What is the least possible value of n? Alright, n is the degree. So they're basically asking us what is the least possible degree we can have with this information. Hey, let's use these blue notes that we wrote down from the previous problem. The fundamental theorem of algebra tells us that the degree equals the total number of zeros, including complex zeros and any kind of multiplicity that you might have. So we can get the least possible degree by adding up all the zeros that we are guaranteed to have. So we definitely have one zero of 3. So I'm just going to start listing off my zeros. So let's see, zeros. We have a 0 of x equals 3 from this. And from this factor, if we set this equal to 0 and solve, that gives us x equals I. I'm going to come back to that. And if we set this equal to 0 and solve, we get x equals 2 plus I. So far, we have 3 zeros. Does that mean the degree is 3? Not so fast. Earlier in this video, I mentioned that imaginary zeros always occur in conjugate pairs. So I see this imaginary 0 right here. If positive I is a 0, then negative I is also going to be a 0. Similarly, with the 2 plus I, if 2 plus I is a 0, then 2 minus I is also a 0. So we are guaranteed to have at least 5 zeros based on the 3 that they gave us. So the least possible degree is 5. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.